Yeah, sure. Okay, next up, our next speaker, which I can proudly present, is Michael Proulx. He's from the University of Bath in the UK, in the Department of Psychology, and is also interested in VR, obviously, and also in cognition and the visual system, if I'm not mistaken. And he also developed some sensory substitution device, or was participating in that, if I'm not wrong here. And his talk is Visual Interactions in Extended Reality. Welcome, Dr. Proulx.
Thank you. Thank you very much for inviting me, and it's a pleasure to be able to see so many great speakers covering such a wide variety of topics. And we've only just begun, so there's a lot more coming this afternoon and tomorrow, so I'm very much looking forward to that. Part of the introduction, so I actually have two jobs right now. So I'm at the University of Bath in psychology and in computer science. But I'm also currently a research scientist at Meta's Reality Labs research in the Seattle area in the state of Washington. All of our labs are actually located in Redmond. Locally, a lot of people call it Microsoft Washington because that's the big tech company there. Nintendo USA is also there as well. I originally started out on a sabbatical in this position there, but now it's an open-ended position. And fortunately, the University of Bath has agreed to that as well. And so I still have PhD students, actually a master's student finishing right now, and some postdocs at the University of Bath for a lot of my work, which is focused much more on assistive technology, inclusive design, and also the psychology and neuroscience side of multisensory perception. And so I'm really getting to enjoy sort of the best of both worlds, being in industry, but also still being an academic. One of the things that made working at Reality Labs so exciting for me was the focus on outreach and publication and collaboration. Originally, when I first went there for this sabbatical, I didn't know what to expect, but I was really pleasantly surprised to see that so many of the other research engineers and research scientists really wanted to work with others to deal with this huge problem space of being able to create all of the virtual reality technology, augmented reality technology, extended reality technology that makes up the metaverse and all these other ways of viewing the technology that we have. It's something one single group of people cannot do. The problems are too enormous. And in the team I'm on in particular, the eye tracking research team, they've developed a lot of open data sharing practices to try and inspire the community to tackle some of these problems, and also had a lot of data challenges as well in order to inspire these two. But what about eye tracking? So there I'm on the eye tracking research team specifically. And why is that so interesting and such a problem to solve? Well, first of all, eye movements themselves are fascinating. We're literally moving our eyes all the time. A lot of eye tracking researchers like to say we move our eyes more frequently than our heart beats. But that's actually kind of like a low estimate. So for example, if you just look at my hand, no matter where you are in the room, while staring at it, you might think you're not moving your eyes, but you are. You're making these fixational eye movements or microsaccades, where you're making these small little movements just to sample things spatially and temporally in a way that gives us the great visual acuity we have. Many of us, like me, maybe with contact lenses or with glasses, but we take advantage of this sampling through the movement of the eyes in order to get this information that we use. And there's an example here in the video where you have a head-worn camera showing where a person's walking, and then a representation down below of what is seen on the region at the back of the eye as a person moves their eyes while walking through this path. Fortunately, we don't experience this chaos because our brain is able to pull together this movement we get from the eyes, the movement of our head, the movement of our body, and develop this perception of space that's relatively stable around us. So what happens if we can't move our eyes? So some really clever experiments going back decades found ways to stabilize an image on the eye. So that way those little eye movements are not registering any change in the image at all, and found that the image would actually fade away. It would fade back in after a while, then it would fade away again. And so without eye movements, we actually lose our ability to see. So what happens if someone actually has a medical condition that doesn't allow them to move their eyes? There's this great paper with Gilchrist, Brown, and Finlay that talked about such a patient who, being unable to make these saccadic eye movements, developed the ability to make saccadic head movements. So in order to get around this problem, they would constantly move their head. In some things, they described it as a bit like a bird. So you'll see birds often shifting their heads as they're looking around. And so the patient had to do the same thing in order to overcome this challenge. So where does this start to come into VR? So one of the exciting things about being at Reality Labs Research is seeing all these new technologies that are coming down the line, including the MetaQuest Pro, which was released shortly after I started there. And now even consumers can have eye tracking amongst a bunch of other really cool technologies available to them. And so it's becoming something that, if you think of all these exponential curves about like VR increasing, metaverse increasing, perhaps eye tracking within that space is something that can be on the increase as well. And of course, the announcement that hopefully early next year, we'll be able to see what the Apple Vision Pro can do is just going to push that even further and even faster. So I really hope they come out on time because I want to give that a try. So when the chief technology officer for Meta, who's basically the chief of Reality Labs and Reality Labs Research, Boz, was asked on one of his Ask Me Anything question sessions about eye tracking, and this is before the MetaQuest Pro came out, he mentioned that they had a long-standing interest. The eye tracking research team had been there back since it was Oculus research. And what's sort of in bold type here is he mentions that eye tracking is super hard. And it absolutely is. And I really like how he pointed out that the degree of biological differences between different people is very, very large. There's a great diversity in the anatomy of our eyes. There is a diversity in the way we like to present ourselves, perhaps with eyeliner or other forms of makeup. Many of you are wearing glasses, and tracking the eyes through a lens that's bending light and causing reflections of light is incredibly challenging. And something that's really important to Reality Labs is that they want eye tracking to work for everyone. So previously, in my lab at the University of Bath, if we did an eye tracking study and it didn't work for someone, they just go in that part of the paper where you say we had to exclude 5 participants. But the company doesn't want to exclude anyone, right? So if you're going to make devices, you actually want it to be accessible to people. If you want to allow developers to know they're building things for anyone, you need to somehow overcome those problems. And the potential applications for eye tracking are enormous. So the reason the company's been thinking about this so long was revealed in a blog post and a bunch of videos and interviews last year, where they note all the ways that eye tracking is important for getting to this point of visual realism they call the visual Turing test on the team. And there's great examples where you have like varifocal technology, optical distortion correction, and many more things. That eye tracking is an essential technology in order to enable just these wonderful displays that we might have at some point. And if you haven't seen it, definitely check out the website. They're really cool. So in this talk, I just wanted to go through a few case studies of some of the research I've been carrying out within this greater context of how eye tracking fits into virtual reality, augmented reality, and just sort of this general space of extended reality. First, I'm going to talk about some of our work on using eye tracking to know where our eyes know where to look next in interactive virtual environments. Then I'm going to describe our research on gaze dynamics in natural active vision, which is a core thing to understand for comfort in VR, but also when we get to augmented reality, we need to know where people normally look, and using our eyes in new ways in VR. Now, a lot of work on eye tracking goes back to work by Yarbus to describe the exciting things that our eyes and their movements reveal about us. Now, what's kind of cool looking back at Yarbus's book is he's dealing with the fact that eye tracking is super hard. And a nice example here is this technology used to keep the head fixed in place. So instead of having to deal with this problem of head movements, he made sure they were secure. And of course, we still do this today. We have chin rests, we have bite bars, all these things to make people feel very uncomfortable, just so that way we don't have to deal with head or body movements. Similarly, he solved the problem of blinks. So dealing with people blinking at the wrong time with eye tracking is terrible. And so he would use this adhesive to actually keep their eyes taped open. And I'm sure most of you would really not want to subject yourselves to that for a long period of time. But what's cool about what he found with all of this was that even if he presented just this painting, a single static image, he would ask people to do different tasks. And when he looked at the scan paths, which are made up of fixations and the saccades to new locations where they would fixate, if you trace all these together, you get this scan path. And these patterns would be qualitatively different across the different tasks, such that by looking at where people move their eyes, you can figure out what their intentions are and what they're paying attention to in order to fulfill those intentions. So we decided to take a look at this, and one of my PhD students from the University of Bath, Jacob, who actually interned at Reality Labs several years ago, and then interned at Microsoft Research, where he's currently a postdoc, wanted to try and get beyond the static two-dimensional nature of Yarbus's work, but get into the interactive virtual environments as a way to better understand where we might look in real life as well. So trying to sort of take it to the next step in that work. And so he did this with a few different virtual environments in order to add more variety into what people were experiencing. They were interactive, so people could move through them. And as they moved through them, they were asked to either just sort of freely view things, which is the most popular task in eye tracking. You just tell people to look at whatever they want. Visually search for specific objects. So they would show an image of, say, a television and then have to find it. And navigation. So they were told they would spawn at the location shown by the green dot, and they had to find their way to the red dot in order to finish their task on that part of it. And so what we wanted to do is try to see what else could we get out of the analysis of eye movements to be able to determine which tasks they had been given. And so there's a lot of different things we looked at. One thing in particular here, just for navigation versus free view and search, were things that, like, people were more likely going to look in the center. So as they're trying to find their way through, they're going to look at the center and the floor to avoid obstacles as they moved around navigating. And also they're more likely to make deeper fixations because they're trying to find that endpoint in the environment. If we compare just the visual search versus free view, we saw things like people were more likely to direct their fixations to the floor. Again, we're simulating gravity in our environment. Maybe if it was an outer space experience, it would be different. So objects you're looking for are more likely to be down. People were, again, more likely to look deeper and make larger saccadic amplitudes because they're looking for things that match the visual features of what they were shown to look for, rather than just looking at, say, anything that happens to be bright and shiny. But that was just sort of a stepping stone, because one of the reasons we did that is because we could have greater control over the environment. We could replay it back and see where they were looking and do an analysis of the images they were looking at. And that was perfect at the time we did this study. But we wanted to get more into what people are doing in natural active vision, which is a line of work that has been looked at for a long time. So LAND in particular has done some really cool studies looking at where we steer when we drive a car, seeing where we look when we pour a cup of tea and do other simple tasks like that in the home. And so we followed this up across a number of real world tasks. And this was done with an intern at Reality Labs, Charlie Burlingham, who is getting his PhD at New York University and is currently under review, so you can find it on bioRxiv. So going back to Yarbus, we wanted to take advantage of this fact that these scam paths arise from user intentions and tasks that they are being given. And in the context of Reality Labs, this is really important for being able to predict where people are going to look for possible applications in AR. So you don't want to have something appear in the middle of your vision if your task is navigation and then suddenly you trip over something. And so you need to have some knowledge of where people are going to be looking and why in order to present things appropriately. So we did this with real world data. We had people perform 9 tasks. So we end up with over 30 hours of recordings across our 31 participants. What we focus primarily here on is having this egocentric scene video combined with estimates of where their gaze was in 3 dimensions. And we had IMU, so we can not keep people on a chin rest, but be able to account for any movements that they're making in the space as well. And we did this with the Tobii Pro 2 mobile eye tracker. And now they have a 3rd generation one, which is really cool too. So what might give rise to predictability for where people will look? Well, if you look back to a lot of human visual attention literature, a lot of work has found that you can predict where people look based on the prior 2 fixations. And mostly what people find are these forward saccades here, where people are more likely to first fixate a location, make a saccade, and the next saccade will be somewhere in the same direction they already looked. And that's as opposed to doing a refixation, where you might start at one location, look somewhere else, and then come back. And so in the psychology literature, that's called inhibition of return, with the idea that it's more efficient if, say, you're searching for something, not to keep going back and looking in the same place you already looked. Similarly, if you're just looking at anything that's interesting, well, you already looked there, so then it kind of gets discounted, and you just keep trying to find the next most interesting thing as you look around. And so in this polar plot here coming from Bayes and Hussein, for example, where people are looking at 2-dimensional flat images, you'll notice that there are more of these forward saccades than these refixations occurring. But in looking at this in real life tasks, we found something startlingly different, which was that instead, you'll notice on these polar plots, all the activity, the higher probability is at the bottom, meaning that people in natural tasks commonly refixate. So that is, they'll start looking at something, look at something else, and then come back again. And they do that more often than they do looking anywhere else, any sort of forward saccades or oblique saccades or something like that. And so in thinking about it, we built up a model that we call the effort minimization hypothesis, which is that people are, what you can think about as maybe inherently lazy, or just we naturally want to conserve energy and be comfortable. And so when you move your eyes off to far eccentricities up to the periphery, you'll start to experience some discomfort. And it takes more energy for all of your ocular motor muscles to hold the eye at that far peripheral position for a long time. And so it's most comfortable at the center of the orbit, whichever way your head is facing. And so this whole yellow area here describes these areas of high effort. You have lower effort here near the center. And so refixations make sense because if you start in the center and go out, you want to reduce that discomfort and move back to the center. And forward fixations, you're going to be going from an area of high effort to lower effort to higher effort again, which will cause more discomfort and take more effort. And so instead, we're more likely to orient our body and our heads towards things where we know we're going to be extracting more information for a while. And so when we put this into the space of our data, where we looked at first the probability of where people fixated and also the duration of fixations, we found that indeed people were more likely keeping all their fixations near the center of their orbit, and those fixations were for a longer duration than those in the periphery. So if they did have to look out in the periphery, they would only do it for very short periods of time and then bring their eyes back to the center of the orbit. And we just created a bunch of scam paths based on this probability. We end up finding that the model did predict that people will be making these refixations. And it actually kind of over-predicts it. So it doesn't show hardly any sort of forward saccades here occurring. But you'll notice in some tasks, like here for walking, for example, a little bit for this working at a desk task, that there are some that occur. And so the model clearly doesn't capture all the data, but it's capturing the primary patterns that we see across all of these tasks. And what's also neat is if you look across these two variables, so the fixation dispersion, which is how far out the eye looks into the periphery, and the fixation duration on the x-axis here, so how long they hold the eyes there, we see that there's a trade-off space between all the different tasks that people carry out, where sometimes when people are walking, they might have to have a greater dispersion of fixations, but then they just don't hold the eyes out there in the periphery as long. But if they're browsing the web on their phone, they'll go ahead and hold their eyes for a much longer period of time because they're only keeping their eyes within the space of their phone, which they can hold near the center. Now, we did that with the Tobii Pro 2 glasses, and something that's been created by Reality Labs that's really cool is called Project Aria, and it's also part of the outreach that the company does. So this isn't a product, you can't buy it, but it's something the company will give to researchers to use as a device for doing any sort of work to understand how people are interacting with their environment. Like Mark in his talk described like life logging, for example. So here you have a multi-sensor device that has a egocentric video camera. It has eye tracking. It has microphones, GPS, IMU, SLAM cameras, and a bunch more. And the team has also now developed a machine perception suite of services to help you make sense of all that data, to be able to better understand what people are doing as they go through any sort of tasks you might give them. And so do check out the website if you're interested, because that is something that's a free collaborative tool for working with researchers. Okay, finally, I want to talk about using our eyes in some new ways. And this is some work we presented at IEEE VR this year and published in the special issue along with it. And for this, and I'm proud to say also, this work came out before the Apple Vision Pro announcement. So we're already talking about how you can use your gaze for interaction. So that is, a lot of people in VR are used to using the hand controllers to be able to interact with objects. And we wanted to explore and work out a good, fair baseline for comparing the eyes to other forms of input, like controller tracking and head tracking, for being able to efficiently do tasks in VR. And so, as you might expect from someone in a background that's psychology and neuroscience, we have these highly controlled stimuli for doing the tasks, where we can make these comparisons between people looking, and in this case, pulling a trigger on the controller for selecting the objects. Another option could have been dwell time, which if a person can't use their hands, then instead what you could do is people have to look at the object for a fixed period of time, and then that selects it. That's another option. The controller, which you use as you normally would, and head tracking, where you turn your head to look at the objects and then pull the trigger to select them. Something important that we notice happens in a lot of studies, particularly studies that say things like the eyes don't have it. So there was a lot of work that was very skeptical that you could use eye tracking as an input device. They often don't report how accurate the eye tracking is. So one thing that's clearly a problem is if the eye tracker says you're looking here when you're looking here, then selection is going to be a problem. And so one thing we've been made sure to do, and we've suggested to others to do, is to always measure and validate the performance of the eye tracker. So that way you know if it's actually good enough to allow people to use it. And again, the individual differences matter here too. Some people, like I said, are easier to track their eyes than others. So with relatively good eye tracking, which we did with this Tobii eye tracker we put into Quest 2s, what we're able to find is in terms of throughput, sort of a measure of efficiency for how much people were able to process per second. We're able to find that the eye performed the same as the controller, statistically indistinguishable, and both were better than the head. So here, higher is better performance. Movement times were similar. So essentially, we found that the eyes were able to move as fast as the controller for being able to select objects. One area that needs work and development is misses. So with the eyes, we didn't provide a cursor because there's other problems that happen where if you have a cursor there and you have a little bit of error, you start to chase it with your eyes. And so we don't have that. We didn't provide visual feedback, but we've done that in some subsequent work. And so you end up with misses. So people end up looking, and if they miss, they end up pulling the trigger more than once in order to hit the target. And so this is certainly an area where innovations in visual feedback or eye tracking that's perfect would allow people to do this without any misses. But what's interesting is even though people had more misses using their eyes in the controller, when we asked them at the end what they preferred to use, the sort of gold medal here went to eye tracking by just a little bit, beat out the controller. So more of our participants preferred it. Controller got the silver medal here in the middle, and head tracking was the least favorite. And if anyone's done any sort of head tracking for a long period of time, you'll know why, because it takes a lot of effort. You definitely feel the strain on your neck and shoulders. Now, one other thing I've been excited about Reality Labs is a lot of the researchers are focused on responsible innovation. And so it was great hearing about some of the different parts on the ethics side of things. And the teams involved in developing the MetaQuest Pro were very much concerned and see it as something that is an ongoing research issue to try and understand how to develop all these new sensors, new technologies, acquiring more data about people, and being able to do so in a responsible way. Another thing I thought was really nice, particularly as someone who's worked in assistive technology for a long time, was this focus on how, well, first of all, eye tracking can be used to interact with content, but also the important note that that could be an accessibility benefit. So if you have someone who's unable to use their hands, for example, you could do gaze targeting with dwell time as a selection tool to allow people to interact in a way without using a controller. And so there's definitely opening up an exciting space. So just to conclude, first part I told you in the empirical part that was about how the tasks we do impacts what we pay attention to in the environment. The second part was about how in natural gaze, we tend to return to locations we looked at before across a variety of tasks. And in the final part, described how users even prefer this unmodified eye tracking we did for targeting, making it an exciting, new, and accessible way for people to interact in virtual reality. And like everyone else, I'd be really happy to hear from you with any questions. You can write to either my Bath email address, my Meta email address, or reach out on LinkedIn. I really look forward to hearing from anyone and having any questions later on. So thank you very much.
Thank you. Thank you very much for your
Thanks.
interesting talk. Shall we announce ahead? I think we don't have questions for him at the time being.
Yeah, you guys know where to find him, right? I mean,
yeah.
So I just wanted to say, oh, by the way, it turned out that we have a live stream on Twitter. I just realized that. I mean, it's probably the first conference I know that has a live